You do have to be careful though. This must have been close to 10 years ago as well. I don't even remember I don't even remember saying it, but at some point I must have said, oh, you get extra credit on the final if you sign your name in blood or something like that. Holy, had a student come up at the final exam to turn it in front of me. He took a knife, took like, I don't know, pocket knife out or something. I had to wait for that test to dry. I couldn't put it in the common pile. This is back when we still took tests with paper. But you can still find him on Nick Yenter was the student's name. He's went on to get a master's degree. I think he's a software engineer for Microsoft or something like that now.
Did you give him the extra credit?
He didn't even need it. He was, I think he maybe got a 98 on the exam and I had to go and nitpick or something like that. Yeah, so you got to watch because you always have somebody in class that will take that too far. Well, it's a good story, but I don't know if I want that to start becoming a tradition. Lippman's hazing his students by making them cut themselves in class. All right. So last time, let me make sure I'm recording. Yep. All right. So last time we were kind of going through the Apple story thing, and we bobbed and weaved into some compiling. So we added some coding stuff into there. We talked about this idea of compiling. So when we turn our high-level program into something that the computer understands. So last time we looked at the hello world in Linux assembly. And I think we also wrote the C++ version of hello world. So you saw that C++ version is, maybe if you've never programmed before, still felt a little intimidating, but in general, looked more English-like than, the assembly language for Linux that was already using power tools because it was already leveraging the system calls of the operating system to accomplish this task. For instance, like syswrite, putting something out on the screen is something we take for granted, right? We don't think about that like, oh, that's something the computers can do just lickety split. The reality is there is a lot of stuff happening behind the scenes in order to get that to happen. Really, for those of you who are like PC gamers, the only reason that even happens, and it's something we kind of left off, we mentioned a little bit with our Microsoft operating systems that one of the problems with Windows 2000 is that it had a naming convention that was in line with their consumer operating systems, but it was based on their business operating system, NT 4.0, which means that it didn't have all the extra driver support in it that the consumer operating system had, because consumers, they're the ones who get 1,500 different printers or graphics cards or all these other things, where business users typically are not, they have a enterprise level stuff and they're not playing video games on their corporate computers, that kind of stuff. Well, so one of the things that would, the immediate problem people ran into is something that worked on their computer yesterday, like a joystick or something, no longer works once they install Windows 2000. Because of these drivers, we have pieces of software that sit between, the joystick, the mouse, the keyboard, the printer, whatever it is, between your $1,000 graphics card. There's something that sits between that and the underlying operating system, so the operating system can tell that piece of hardware what to do using all of the magic tricks it brings to the table. You might imagine that when you go out and buy a $1,000 NVIDIA graphics card or a junky ATI graphics card. Any of you ATI fans in here? NVIDIA fans? Have no idea what I'm talking about? Half the class. So, no, ATI is junk. They've just recently caught up, but NVIDIA is the better graphics card company. But in any case, do you think that $1,000 graphics card probably has some capabilities built into it that maybe the onboard Intel graphics on your laptop or something doesn't have? Sure, and that comes with the cost of making it and also the physical footprint, right? You know, the built-in Intel graphics card in all your laptops, if you don't have a gaming-centric laptop, is something that fits on a little tiny chip. Where if any of you have, you know, one of these gaming PCs with a graphics card in it, some of those graphics cards are like this long, right? Probably about that thick, got big honking fans on it all over the place, right? Most of them have lights to make it look cool, right? And you plop it in there and you need to get this giant power supply for your computer, you know, because most of your computers ship with, I don't know, it's called a 200-watt power supply or something on a desktop computer that's meant for business or something. But if you're a PC gamer, how many of you are PC gamers who built your computer? What power supply we have? Anybody have a kilowatt power supply? 750 watt? 750 watt seems to be kilowatt. Anybody kilowatt? Yeah. So my gaming PC, while I do a VR, I have a 2 kilowatt power supply. I have a 24090s.
Exactly. That's there you go. 249.
Yeah, you still don't need 2 kilowatts. That doesn't mean you shouldn't have 2 kilowatts. Right. It's like the geek version of like the sports cars. Yeah. Things gets half a mile per gallon. It's a V70. And I only play Angry Birds on it.
On your VR? You're kidding.
Yes, I'm kidding. My power bill's like, it's not like 400 a month or something. I got a big house with lots of stuff. My massage chair uses as much electricity. Stay in computer science. One day you can be a professor at a Christian school too. All right. For golf?
Yeah.
Right now I'm playing Stealth, Irons. I get a new set every 2 years or so. I don't do every year.
Those sets last you like 10 years.
No. No. And I get a new smartphone every year. Then I use the previous years as a soap dish. I used to start with it in the shower, but that wasn't working. Well, these make great soap dishes. If we leave the case on, because the soap kind of floats around on top of it, but hits the edges. Now, the real kicker is you're wondering, like, okay, he's probably serious about most of what he's saying. The real question is which of those things were made up? And I'll tell you, it's not the ones you think. Soap dish is real. All right, so we were talking about, as we get off track and come back, we're talking about the idea of compiling, where we like to write, human beings like to write stuff in this high-level language like C++, which I promise will become friendlier and friendlier to you. But we certainly don't like that underlying assembly code, even if it's using the power tools of our operating systems, like those system calls or the driver system that teaches your program how to talk to that external graphics card. You know, in order to get something to show up on your screen, to get hello world to show up on your screen, your operating system had to send the information on to the driver for your graphics card, which then had to send it out to your NVIDIA graphics card, either using hello world, only had to use the old, you know, that doesn't require any 3D acceleration or anything like that. So it was able to speak old VGA language. But still, you know, there's lots of handing off and conversion stuff that has to happen behind the scenes in order to ultimately get something to appear on the screen. It doesn't just happen. All right. In the early days, our computers, when we were talking about turning on the vacuum tubes, the light, you didn't have a monitor. You know, just other light bulbs would turn on. That was your output. You want to add two numbers together, you turn on the right bits with the vacuum tubes, and you look at your answer row of vacuum tubes, which tells you that this number plus this number equals this number. That was how using a computer used to work. Okay, so we've come a long way, and realistically, many of us take for granted what our computers are doing for us that they didn't used to do. A monitor wasn't even a thing a long time ago. All right. But in any case, we like power tools. So we have this tool called a compiler, which takes our high-level programs that we like to write and converts it into something the computer can understand so that we don't have to. All right, we saw an example of that last time. We started talking about 3 kinds of programming languages. Ultimately, we have machine language, the zeros and ones on the computer. We have this low-level language, which is like the assembly language we looked at last time, where every line of code is equal to exactly 1 magic trick on the CPU. We were able to follow it. It wasn't horrible for us, but it's something you probably would not enjoy writing on a day-to-day basis, right? We like the high-level languages where we write 1 line of code and it translates into a whole bunch of junk that makes us look awesome under the hood. In fact, one of the jobs of a compiler is to turn a bad programmer into a better-looking programmer. So you can write inefficient, accurate code, and it'll, under the hood, potentially turn it into more efficient, accurate code. Now, it won't take inaccurate code. If you give it a whole bunch of syntax errors and stuff like that, it won't magically just fix those. All right. But anyways, we like high-level languages. So one window we can look at programming languages through is which type of programming language are we dealing with? Are we dealing with a bunch of zeros and ones? Or are we dealing with a high-level language? 99.9% of the time in your industries, you'll be dealing with a high-level language or potentially even a level up from that. Like I mentioned, in the second half of next semester, we'll be using Unity Game Engine, where you'll still be working with a high-level language when you write scripts. But a lot of the stuff you're going to be doing is just dragging stuff out on the screens and clicking some buttons for turn gravity on, that kind of stuff. All right, so you're not even using a language at that point. That's actually one of the first things you should write in VR that we wrote when I was teaching a VR programming class with Game Engine, is you procedurally generate a giant tube, think it like a water slide. And then you put the VR guy in there face first and then turn gravity on. So you got the headset on, you're at the top of this tube, and then it set it up vertically. So you fall through there. You're bouncing off the walls. So all the physics is turned on for you. It's a program. It takes 10 minutes to write. Yeah, and it's just meant to get you sick. Yeah, we would set it up before an exam, and whatever student could last the longest at it, we give an A in the exam. Everybody else has to take the test. Is that true? I have the GitHub link to the. All right. So we're talking about the Apple story. We all became convinced that Apple died a long time ago, and what we see today is actually Next computers with an Apple logo on it. Even under the hood at their software level, they still have next step stuff from Next computers. All right. This is when Apple acquired Next computers, which came with Next computers CEO, which was Steve Jobs. They installed him as the interim CEO, later called the iCEO, because this is during that season when Apple came out with everything that was i this, i that. So iPod, iPhone, iPad, iMac, iBook. The iBooks were really cool laptops. They used to have a little handle on them. They were all colorful and stuff. This was back when they were still using PowerPC processors. We talked about that a little bit last time as well. Talked about 2 bullets that Apple really dodged after they almost failed it. Well, really, after they did fail it as a company and just rebranded Next Computers. But their first thing was they decided, hey, let's not be proprietary. Let's go ahead and sell Apple clones, or allow other companies to sell Apple clones that ran our software. OS 9 wasn't stable before. Now you're having it run on other people's hardware. I mentioned that Apple's solving a much easier problem than Microsoft is. Microsoft's writing an operating system that runs on 1 million different computers. Apple's writing an operating system that runs on like 8 computers. Okay, so I would argue that, yes, I have less problems with my MacBook with the operating system crashing or something. I probably reboot my machine twice a year or something like that. And it's usually for software updates. But that's because the software is running on 8 different computers, whereas Windows is solving a much, much more difficult problem. All right. So anyways, Apple dodges 2 bullets at some point in time. They first alienate their user base by coming out with Mac OS X, written for the PowerPC processor. So that's a non-Intel processor. So overnight, all the people who upgraded to Mac OS X had all their software stop working. Microsoft Word no longer launched because Microsoft Word was made for an older operating system, a different set of system calls. Same architecture, Mac OS 9 ran on the PowerPC architecture, but ran on the OS 9 set of system calls. OS X initially ran on the PowerPC architecture, so the same architecture, but a different set of system calls. So that gets back to this idea of compiling, and we looked at that last time. The code we looked at last class, the assembly code was Linux-based assembly code, so used the system calls of a Linux operating system along with the Intel architecture. So if we took that same program and we tried to run it on a Windows machine running on that same Intel architecture, it would not work because Windows system calls are different than Linux system calls. So both of those things need to line up in order for a program to be executable. So all those Mac users were running Microsoft Word that was created for Mac OS 9 system calls, but the PowerPC architecture. And then the next day, they now have basically Unix system calls. Mac OS X was not an upgrade to OS 9. It was a new operating system base. So all their software stopped working. As you imagine, that didn't make them happy. They shipped those computers with a virtual machine called the Blue Box, one of the early virtual machines that, so you launch OS X, you had 3 applications that ran natively under OS X, and then the rest of your stuff you emulated inside of OS 9 running inside of OS X using 2/3 of your system resources. Now, not a big deal if it was 2 weeks before the software gets updated, but of course it wasn't. It was something like 8 months to a year before the software got updated. And this is following a year and a half after the a fun I guess joke. If you go back and look at one of the Apple G4 processor commercials, you can find them on YouTube, I'm sure. You know, they released a computer with, we talked about multi-core processors, right? They released a computer that was a dual processor machine. So this is before we figured out how to get multiple cores on a single chip. Apple came out with a machine that had 2 physical chips. You know, 2 heads are better than one. And it was, you know, Apple would talk about this as the first supercomputer based on some number of teraflops or whatever. And the commercial had tanks. So you always look more powerful if you have tanks, right? But the ha-ha part of this was that they never talked about inside of the the commercial or anything, is if you had a Mac Pro G4 and then you replaced it with a Mac Pro G4 dual processor, for 99% of your applications, it was no faster because OS 9 did not support multiple processors. So they were selling a computer running an operating system that did not support the new hardware that they were selling. It's awesome. And people bought into it. They don't even check. This was before Google. We didn't have the Google. I think we had Lycos at the time. Yeah, much older search engine, or very early days of the internet. But in any case, finally, once they moved to OS X, it supports 2 processors. So at least they got that. Mac OS X did support multiple processors. It just stopped supporting all your software. So you got the double whammy. So in any case, Apple somehow dodged that bullet of inconvenience with the new operating system. Then finally, they have OS X running on the PowerPC processors with all the famous software ported. So everything was working now. Everybody was happy. OS X was a great operating system. Things were really chugging along pretty good for Apple. You know, they were making money hand over fist with the iPod. I think iBook was already out. iPhone probably had just been released, somewhere in that ballpark. So, you know, they're doing pretty well. They're no longer failing as a company. They're doing pretty well. Well, then all of a sudden, Apple just out of the blue decides, oh, we're just going to switch to Intel processors. So instead of the IBM-made PowerPC processor, again, the architecture of the computer, they changed the architecture. When they came out with OS X, they changed the operating system calls, which broke compiling, right? Then once they waited for all that to get fixed, then they go and change the architecture. So all that software that had just gotten fixed is now broken again. Because Apple, you buy another Apple computer the next day, it's still running OS X that's now been ported to Intel-based software, or Intel-based hardware rather. But now all your software was made for OS X running on PowerPC architecture. Software breaks again. Why would they do this after they dodged the old bullet? But they did it again. Dodged the bullet again. So up till a couple years ago, if you were to go out and buy a new Mac, actually even today, if you buy an iMac Pro, it's still running Intel stuff. So we're still in the middle of the transition, but we're on the tail end of it. But up to a couple years ago, any Mac you would buy would be running an Intel processor. Same architecture that's inside of any of the Windows machines you were buying, but a different operating system, right? So the system calls would be different. So that's why the software doesn't just universally work between them, but they're on the same architecture. But things are going pretty well for Apple for a while. Intel seemed to be making good processors or whatever. And then all of a sudden Apple decides, oh, we're going to go back and just start making our own chips. I'm sure they just bought some processor company that makes, because all of Apple's commercials or their keynotes talk about, oh, everything's built on top of our own silicon. It sounds cool when you say that, right? It sounds geeky. But really, Apple's just making their own processors, and it's probably a company they bought that's making their processors. And those processors really started at the iPhone level. So Apple didn't have their desktop processors running their own stuff until more recently. But for many years now, their iPhones have been running some kind of custom processor that Apple created that is battery efficient and all that jazz. Well, now they've moved basically all their laptops over to either their M1 or M2 architecture, and then they did turbo mode on those with the M2 Pro, M2 Max. So very, very powerful chips, built-in graphics cards. So great for portable computing because now you don't have to have that big honking graphics card. It's just built onto the chip. Now, is the graphics on a M2 Ultra as good as the latest, greatest NVIDIA graphics card? No, but it's shockingly close. So if the best NVIDIA graphics card right now is a 4090 Ti, I bet you the graphics on the highest end M2 stuff is probably like a 3070, 3080, if you follow in NVIDIA stuff. So still, you know, pretty solid when the thing just lives on the processor. So anyways, now Apple's back to running their own hardware, which means that it's no longer compatible with the old stuff, but there was a switch here. All of your stuff, though, Apple learned their lesson, or at least technology advanced enough where all of your software, if you went out today, if you're running an Intel-based MacBook, and you went out today and bought a brand new MacBook with an M1 or an M2 processor in it, your stuff would still work. Because built onto the processors, it has a translation engine, which on the fly converts between Intel assembly and Apple architecture based assembly. You're losing a little bit of performance, but it's doing the conversion at the hardware level. So in any case, it's didn't cause the same problem hysterically caused. What is kind of exciting in the technology world right now, though, is the Apple processors are actually shockingly good from a performance perspective. And that kind of benefits us as consumers because obviously not everybody's running Macs. Probably most of the computing world is still running Windows-based machines. And I don't necessarily think that's going to change. But what now has happened is now Intel has had a fire lit under them because they've been surpassed in terms of processor technology. AMD was really already chasing them pretty hard for a while. Then Intel made a jump with their i9 processors and probably retook the lead as long as you weren't looking at the power bill. But from a power perspective, horsepower perspective, the Core i9s are better than any of the AMD processors for single core, or let's say up to 8 core processing. AMD has some top tier, 48 core processors that are very, very good at very specific tasks. But architecturally wise, Apple is currently the leader in PC architecture, or in CPU architecture, I guess, whether it's for a mobile device or a laptop or a desktop. So now Intel has to play catch up, and typically these innovative companies have really, really smart people working for them. And when they're backed into a corner, they'll come out with something really cool. So chances are the future is pretty bright for processors, because Intel won't be able to just keep coming out with this year's Core i7 that's basically last year's Core i7 with 20% markup, and we've just discounted last year's by 10%, and we don't care what you buy, just give us your money. All right. So we just talked about this M1 chip, M2 chip stuff. These are Apple's processors using their own tech and not compatible with Intel. So new competition, good problem to have. All right. So that pretty much takes us through our Microsoft and our Apple story to get us where we are today with our hardware. For those of you who run might as well go ahead and update that, a Mac, but also want to run Windows, the software I use is called Parallels, but there is free software, VirtualBox from Oracle, that you can install Windows on your Mac, and it runs shockingly well. So I historically would have looked at a Mac for 2 machines so here's Windows 11 on my computer, and it's just swipe between. I would have historically looked at a Mac for as 2 computers for the price of 1.8, but now it's kind of like 2 computers for the price of 2.2. The math doesn't work out as much anymore, except for I only have to carry 1 machine around. All right, let's look at some more coding stuff. So I mentioned there's 3 kinds of programming languages: machine level, low level, and high level languages. So there are 3 kinds of programming languages. So we're looking at these from some different lenses. So we have interpreted languages, we have compiled languages, and I'm going to go ahead and I'm going to say we have functional. I'm going to leave those out. We're going to say this is 2 kinds of programming languages. Good enough. So interpreted languages and compiled languages. Well, we already talked about the compiled languages. We have a relatively small set of compiled languages because these are much, much, much more difficult to write, compiled languages. So those are C, C++, Java. I'm just going to throw a little ish in there. Mostly Java is a compiled language, but we'll talk about that here in a few minutes. Any .NET language, so C#, Visual, C++, etc. Objective-C, and Swift. I think it covers them. I'm sure there's some, weird compiled languages out there that doesn't cover, but 107% of the jobs you find out there writing code for compiled languages, and the math checks out, trust me, will be one of those. I would say your most popular jobs out there today are C++, Java, and .NET C#. Swift, you'll see only if you're looking at iOS development type stuff. So compiled languages, these are languages that convert the high level code to machine code prior to running the program. You compile once and then can run the compiled program over and over. These languages also tend to be faster. Interpreted languages, these require an interpreter. This is no different than if somebody has a speech they've written in German and they send it to a news station who then has one of their people on staff who speaks German and English interpret and convert the speech over to English so that it can be read on air or something like that. It works, but that takes more time, right? There's an extra step there because you have to take. So this converts a high-level language into something understood by the interpreter during runtime. Okay, which is, after running the program. So you start running the program and it immediately starts going through the interpreter. So every single time you run the program, it goes through the interpreter again, rather than pre-interpreting it. Compilers pre-interpret, interpreters interpret on the fly. So we would say these guys are relatively slow. Now, the reality is those computers are really, really, really fast. So a language that's fast versus relatively fast versus relatively slow is probably always going to feel very, very fast to the common person. Outside of more extreme use cases, for instance, like video games and operating systems, things that are really trying to maximize the performance of your hardware. Whereas generally speaking, your hardware is not being taxed very much using normal processors or using normal computer programs. So whether it's a compiled program or whether it's an interpreted program, your computer sits there idle probably 98% of the time. And if you're a gamer, the only time your computer is using anywhere close to 100% of the resources is while your game is running. As soon as you switch back to checking email, it's barely doing anything. All right. So one thing we then see is interpreted languages are a dime a dozen. There's zillions of them. All right. You have heard of some of these. So some languages that are interpreted: Python, JavaScript, PHP. What else I want to throw in there? I'll just leave it at that because we can go on for a while. So those are some popular interpreted languages. Python, JavaScript are really used heavily. Now, one interesting thing for those of you who ever get into web programming. Any of you done any web programming in here that's used things like Ajax or jQuery, Angular, React? Then insert 4 zillion techie, geeky sounding terms. So we could pretty much say all web-based interpreted languages. Well, I'm going to say nearly all, just so there are PHP would be an exception, but it's a pretty old exception. So nearly all web-based interpreted languages are special libraries built using JavaScript. So really, any new language that comes out has a high chance of being interpreted and has a high chance of just being a special JavaScript library. So today, if you're a web programmer, the current technology war is between React, which was a Facebook product, and Angular, which is a Google product. And both of these are solving an old problem. If you go to a website, watching sports scores, something like that. Let's say you're following the latest Packers game or pick your favorite team, whatever it is. And you go to the web page for the scoring. Today, we expect that score to update live, right? Right. Well, once upon a time, you used to have to keep hitting refresh over and over again to see when they finally updated the score. So we can use that as a case study here. So how do websites update automatically? So early days, they didn't. Human hit refresh. All right. But then they came out with a library called Ajax. So this was a JavaScript library that reloaded only a certain section of the web page without reloading the entire page. I'm just going to say somewhat cryptic to use, but solve the problem. I'm going to say always received its new content from the backend server. We go back a slide here. Types of developers. We have front end and we have back end. What's a front end developer? Good. Probably the interface. So front end is what the human being sees. Back end is what is behind the scenes driving the user interface. So historically, we would say something like front end developers are mostly a design skill set with a little programming skill set. Typically, front end leverages JavaScript for making sure you filled out web forms before submitting to a server. There's a little bit more to that, but I think that largely captures the programming side of a front-end web developer. You put in the code necessary in JavaScript to make sure that when you hit the submit button on like the please enter your username and password form, if you didn't put a username or a password form in, it would catch that before it ever tried to send missing data to the server. This was especially important when the internet was much slower and we didn't want to use up, precious bandwidth sending a request that we knew was going to fail. All right. So that's what the human sees. But now, as the difference between front end and back end has become kind of blurred, I would say that the typical description of a front-end developer has not necessarily changed. They're probably, as you said, doing user interface stuff. It's still about what the human being sees with some very light programming. But now the responsibilities of the back-end developer. So used to leverage web server based technology, which would respond to what's called an HTTP request from a web browser. Let me stop this for a second. We're going to draw a picture here. Web development is just like PC development. There's some kind of workflow. We're going to look at what that looks like for us to really understand this front end versus back end, because it does put us into a position when we're, again, I've mentioned that programming is the skill set, the language doesn't matter, but you still want to pick the right language that lends itself to whatever problem you're currently trying to solve, rather than trying to force a square peg into a circular hole. Okay. So let's look at how web works. So we have, in terms of network programming, something called the client-server model. All right. And then there is communication, typically two-way communication. Between the client and the server. And we might say, let me hide this. So this is a request. And this is a response. All right, so we can think of the client server model generically as what happens at McDonald's, right? You walk in, you're the client, they're the server at the kiosk or the person you're placing your order. You say, I would like to request a Big Mac, and you send them some money, and their response is, here's the fish sandwich. Ever had that? You get the entire, like, it's shocking how often the order is wrong at McDonald's. It really is. But in any case, you have client server model, you make a request, you get a response, move on with life. All right. You'll find out that a lot of our technology things are modeled after real life things. Because one of the things we talked about that a programming language does, it allows us to tell this computer what to do. All right. So when a human being is talking to a computer, we use a programming language. Well, here, we can just use this. Well, I'm going to copy it anyways. So in our McDonald's example, the client is the customer, the server is the McDonald's employee at the cash register. In the web world, your client application, the application that sends the request to the web server, is the web browser. So this is like Chrome or Microsoft's browser, Safari, so Edge, or if you go older, whatever, in Microsoft's browser. So the web browser makes a request to the server. Our web server usually comes in a couple of flavors. Web servers are either Apache or IIS, Internet Information Server. So most servers, the physical computers that are on the internet that are built with lots and lots of hardware in them to serve multiple users at once, Most of these guys are either Linux-based machines, Linux, Unix-based machines, or they are Windows Server-based machines. If they're Windows Server-based machines, there's a high likelihood they're running IIS, which is Microsoft's web server. If they are on any other computer, there's chances are they're running Apache web server. Now we have some newfangled technologies. How many of you have heard of something called Node.js? All right, so Node.js is a language used for writing APIs. It starts blurring the lines that we'll talk about here in a second. But for that, you have a built-in web server called Express. That's a function of Node.js. So you can just say, I want my program to launch a web server and do something, but there's some limitations to that. But in any case, in our normal model, right now I'm sitting in front of my computer. If I go into Chrome and I go to Amazon.com and I put something in the search box, my browser is sending a request that says, search for tennis shoes to Amazon's web server, which then is going to go in the back end. So this is front end, this is back end. So front end, put that above it here. Back end. There's some other things you might hear this from. This might be called client side versus server side. Kind of means the same thing. All right. So now this communication here in a client server model relies on this client and this server having a language that they've decided they're going to use to communicate, right? When you signed up for this class, you probably assume that the language we're going to be using is English, right? So all of you came to class expecting to ask questions using English and get responses using English, right? Okay, so that's the language that we've chosen in our client server model. Now in a computer, English is probably not a very good language. Okay? English is great for human beings because we're super smart and we can fill in the gaps. We don't need the level of precision that a programming language gets. English gives us a lot more power in terms of expressing vague ideas as opposed to strict detail. Make sense? All of our natural languages do. So replace English with Spanish, German, whatever. They're good at that. They're less good at precisely giving something to a computer without some middleman, like we're seeing now with like ChatGPT and things like that. And that's where things start getting scary. But in any case, anybody know the language that is spoken between your web browser and your web server? The hint is it's not English. Something called HTTP. Anybody know what HTTP stands for? Hypertext Transport Protocol. In computing, whenever you see the word protocol, that's a synonym for language. All right, so we have a special language for transporting hypertext. And what's hypertext? You go into a web browser, you right click, you say view page source. This is an example of hypertext. An HTML document that has a bunch of opening tags, closing tags. At some point, we'll talk about XML versus JSON and that kind of stuff. But for right now, we'll just call this hypertext. All right. Now, we did mention that programming languages have facilities for remembering stuff, asking questions, and repetition, right? And I think I probably made the comment at some point, usually when I ask a group, how many of you have programmed before? Well, some people might raise their hand. And then when I say what languages, they might say, oh, HTML. Yeah, well, if you did like a web page or something like that in high school or whatever. HTML's a perfectly reasonable data representation language, but it's not a programming language. Why? Because it doesn't have facilities for remembering stuff, asking questions, or repetition. It is about making things look pretty. Okay. So when we talk about the web browser side of things, the web browser understands HTML. So whenever it also understands JavaScript. Now you've been to a web page before. I mentioned it even here a little bit where it's asking you for your billing address, right? And you only fill out half the form and you hit submit, and it pops up with some kind of error, gives you some red stuff saying you need to fill out this entire thing before we can create your account or we can make your purchase, whatever. You've seen that before? All right. So that means some level of programming happened on that front end in order to go through and ask a bunch of questions about, did they fill in this box? Did they fill in this box? Did they fill in this box? Keeping account of how many boxes they didn't fill in, remembering if the number of, and then being able to, remembering how many boxes they didn't fill in, and then being able to ask the question, if number of boxes they didn't fill in is greater than 0, scream at them. That's all programming stuff. Remember things, asking questions, repetition, okay? But web browsers, we just saw, they interpret HTML and make it look good on the screen, pretty pictures, text, that kind of stuff. So since a web browser uses the language HTML, and HTML is not a programming language, if we want to do programming-esque things on the front end, we need a programming language to accomplish that. That programming language is JavaScript. The very, very early days of web, we had 2 competing languages on the front end. Anybody know what the competitor with JavaScript was? A language called VBScript, which later became known as Active Server Pages by Microsoft. They moved it to the back end. So it was a Microsoft technology. So it became Active Server Pages, but that is a back-end technology. In any case, today, any code, any computer programming logic that occurs on the front end inside the web browser is done through JavaScript. Okay? So 2-step process. We have an interface builder that is HTML, interface building language that is HTML, and then we have a programming language for, generally speaking, at least historically speaking, we'll call it light programming, okay? Because typically the programming that I keep harping on, which I don't want to belittle it because it is more than this now, but is making sure you filled out a web form, that kind of stuff. That way we're not wasting requests to the server. If you press submit on this web browser, you don't want to send a request to the server that's missing data. So we're going to check it on the front end here before we send anything over the internet asking for something that we know will fail. That just makes sense, right? Especially when you consider that, a web server, they come in all sorts of different flavors, but one example of a web server, when we go to www.google.com, that's going through something called DNS. It's finding the IP address of Google, all right? And we're talking to one of Google's computers, probably one of their server farms. So some computer that then hands it off to one of their computers that's less busy right now. But regardless, how many requests per second do you think Google's web server gets? A lot, right? And I rounded down. All right. Now, if you are writing an application using Node.js that I referenced a little bit ago, and you're just testing it, and you have 1 or 2 friends testing it, and you're running it off your Express web server that's built into Node.js, you're maybe getting 0 to 3 connections per second or something like that, right? Not really pressing it, not a big deal. All right. But Google, they're handling millions of requests per second, correct? So we probably don't want to send frivolous requests to a web server that we could certainly on the front end determine whether or not this is even has a chance of succeeding. Okay, because when we talk about Google, their web server, let's just pretend like it's a single computer, even though it's an array of computers, but it's a single collection of resources. All right. That guy still has a finite number of resources available to it. It can only do so much. It can only handle so much, right? It can handle a lot because it's built for the traffic that goes to it, but can only handle so much. Now, if there's a million different computers all making requests to Google any given second, that means there are a million web browsers. Let's just keep it simple. Million computers with a million web browsers that each could do a little bit of pre-checking, which is not going to push this computer very hard. So it just seems like a reasonable thing for the client side here to do some double checking for simple stuff before we ever send something to the server. Make some sense? All right. So JavaScript is the language that we use to do that on the front end. It gives us programming ability. In fact, any assignment you get in this class, you could, because programming doesn't matter. I mean, in here we're writing in C++, but you could write the code in JavaScript and then test it inside of any web browser. You could open up Notepad on your computer, type in the program inside of a script tag in HTML, load up the page in your web browser and see the output. It's completely doable because your web browser is effectively a JavaScript interpreter. JavaScript is an interpreted language. Okay. All right. So this is the cadence. A web browser makes a request using something called HTTP, speaking the HTTP language, the HTTP protocol. And then that response gets sent back as HTML/JavaScript. Because that's what a web browser knows what to work with. All right, questions about anything on here? How many of you have heard of something called an API? What's an API? Any guesses? Go ahead. Okay. So an API, abstract programming interface, effectively, it is a tool that lives on a website. Website's probably a fair assessment, but let me kind of draw a picture here that sort of mimics that. And I'll give you an example based on something that I recently mentioned, plus something that's kind of poignant for today's world. We're going to say API example. All right. So you have your client. So we're going to say this is going to be your computer program. So you got your computer program running on your computer here. Okay, that's your client side. Not a web browser necessarily, but this is some piece of software you're writing yourself. C++ program, Java program, whatever. All right. Then on the server side, we have something that is serving an API. This is actually still a web server. I'll talk about that here in a little bit. Okay, but this is still a web server. So this computer program makes requests to this web server. And typically this guy will have a collection of endpoints for doing different things. So, for example, there is a API for like Pokemon cards or Pokemons. So you can ask it to give me a list of all the Pokemons. You can then say for, Pokemon with ID 123, give me the attributes, that kind of stuff. So you can ask it for multiple pieces of information. Okay. You can also, through an API, send stuff to the server side for storing things. All right. So for instance, if any of you use the mobile app for Blackboard, that app uses Blackboard's API. So you have to log in, but then what it does is it talks to the Blackboard server on your behalf to pull down your list of classes you're in. And then the homework for those classes and the grade book and all those things. It pulls all that data in. And if you use the app to submit an assignment or something like that, it pushes that submission up to the cloud, up to Blackboard, and stores it in the database and all that stuff. So it's a two-way communication street. All right. So APIs provide services, both getting data and also receiving data. Now, in the old days, and this kind of is related to what we talked about last time with Mac versus PCs, and one of the goals of Next computers is, historically, we've always had kind of this an issue we've always chased from different directions on the I lost my track of thought. Hold on. And the compatibility of things. So we talked about Mac and PC, how sometimes you would try to open a Microsoft Word document on a Mac using an old floppy disk that was formatted for PC, and it would say, I don't even know how to talk to this thing. Well, that problem pretty much has gone away now, but with modern computer type stuff, we if we're talking about APIs, in the early days of APIs, when places wanted to make their data available, whether, they had 10 different websites, each one would follow some different standard. They would invent their own protocol for talking to their API. So every single time you wanted to talk to a different website or talk to a different data source, you would have to make sure you followed their made up gibberish language for asking for the data. Okay. Well, over the years, as with most things, we kind of come into some standards, right? All right. So let me go to this guy. How many of you have heard of something called a RESTful API, or sometimes these are just called REST APIs? Have you heard this? Seen the phrase at some point? Pretty much all modern APIs will be RESTful APIs. All right. So what does that mean? Now, this is kind of where it becomes sort of funny how in our mind as technology people, we always assume that anything new is brand new and was just invented yesterday. Where with APIs, I mentioned in the early days, so early APIs used proprietary protocols for speaking to the API. So you had to use a different language for every API you talk to. Then we next we created called it a HABZ. Is that a word? There. So it's a HABZ approach. It's spelled correctly. That's the AI. So we create a HABZ approach called SOAP. So we've made the full connection to the iPhone SOAP dish now. Right. So, and SOAP was kind of an initial stab at a standard for APIs, but there were kind of 2 or 3 different versions of SOAP, and no API really followed it to the T, because most of the people who were writing these APIs were kind of still stuck in this like proprietary world, and they only updated their code so much. So even in the SOAP era, you had some incompatibility. Today, we use RESTful APIs. And this is where it kind of gets funny. I mentioned a little bit ago the idea of this thing called HTTP, Hypertext Transport Protocol. All right, this is the language that web browsers speak to web servers. Now, as far as the internet goes, how long has the web been around? Just as long as the internet. Day one of the internet, you had web stuff. In fact, the internet was born out of the HTML data representation language. The early internet was a bunch of research schools, including University of Illinois and as well as Madison, UW-Madison. So big research universities creating some sort of communication network between them for academics to share research with each other. And the language that was invented for sharing data between them was HTML. All right. So the early days, basically the web has existed as long as the internet. In fact, we can even say that the web was the early pre-evolution of the internet. Okay. So this guy's been around for a while, HTTP. Now, HTTP has, if you've ever done any web programming stuff and you've created a web form, you had form action equals ... something like that. And then somewhere else you had a slash form. Any of you ever written HTML that had forms in it? You can tell me what kind of stuff you put here inside of action. When you have a web form, there's usually a submit button, right? Okay. Typically, historically, you would put one of 2 words in there for the action on a web form. You either put get, that guy, or you would put post. Get versus post. For actions. So every single one of you has seen the result of this before, even though you didn't necessarily know what was going on under the hood. So how many of you have been on a web page before where you had to fill out 2 or 3 different text boxes with some information? And you hit submit, and on the next page, you saw several of the pieces of information that you had put in there up top inside the URL. Like it would have blah, 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 .whatever.com, and then be a little question mark, name equals Mike, phone number equals this. It would be all up there in that URL. Have you seen that before? Okay. Get requests, send data packaged inside of the URL string. Because effectively, when you have a web form, think back to the early days, the people who made those web forms. You have 3, 4, 5 pieces of information you're collecting. You hit submit. You have to have some way of sending that information to the next page, right? That's the whole point. You're filling out this form, hitting submit with the hope that that gets sent somewhere. And then you get a response to get something new on the screen that isn't bad username and password, whatever. Okay. So a GET request just stuffed all that stuff up in the URL and said, let's go ahead and send this. And that's where you can find it up there. You can extract it from the GET request. Not a big deal. Gets the job done. Probably don't want passwords and credit card pieces of information floating around up there, but you could, right? Just don't want a shoulder surfer. A post, package data as part of the HTTP request object. So you do not see it up top in the URL. Instead, that data is being packaged along with, well, being packaged up before that request is sent. So you could almost think of that as being sent behind the scenes. But that doesn't necessarily mean it's being sent securely. How many of you have heard of a tool called a packet sniffer? When you have the security class, you'll learn about packet sniffers, where you have a network, internet, whatever, computer network, and the way stuff gets sent over a network is through a bunch of packets. And a packet sniffer lets you look at inside the packets and see the data. Well, your credit card information is going to be sitting inside of one of those packets inside of plain text, unless you got that little padlock on your screen that encrypts it. Make sense? All right, so let me just put a note. Start here. All right, I'm going to put up a short assignment related to RESTful APIs. I know we're not quite at programming yet, but kind of like a one-page paper type thing. I just want you to look into it. You don't have to follow any APA standards or anything. Just kind of a graded activity for being prepared for Tuesday's class. Sound good? I'll put that up on Blackboard today.
A random package from Starbucks ends up on your desk and you get extra credit.
Maybe. Does it have human blood on it?
You take the bowling lane.
I bleed every other day in football. I can make that happen.
What position do you play in football?
Find out.